Okay, so finally, multiplication rule. We have dealt with, also known as the product rule. We've dealt with probability trees. And now the student will be able to determine whether events are independent or dependent. Two events are independent if. Okay, so a lot is going to be thrown at you right now. Probability of A given B equals probability of A. Now that is a logical, intuitive definition of independence. Probability of A given B is just the same as the probability of A. It's kind of like this given B thing doesn't even count because it doesn't matter. Probability of A is just the probability of A, whether B wants to do this or that. Well, the second equation says that you can flip the symbols, and then we have this. It's not a very good definition, but it is true, and it is useful in probability problems. Probability of A and B is probability of A times the probability of B. Now, remember what we said before, that in general, probability of A and B is probability of A times probability of B given A. But this one, there is no given A. It's just the simple probability of B. And so that's true. You can just multiply the simple probabilities if the events are independent. If knowing whether one of them happened doesn't have any effect on the probability of the others happening. Now, all three of these statements are equivalent. They all come from, well, algebra on this sort of equation. But if these things don't hold, which if one of them does, they all do, if these things don't hold, then A and B are said to be dependent events. So we might think of this as a formula for probability of dependent events, but actually that would show a little bit of a shallowness of understanding, because this equation is true for any events A and B, whether they are dependent or independent. Now, if you have to get probability A and B and the events are dependent, then there's no choice to the matter. You have to use this formula. But if they are independent, then you've got this one available to you, which actually is just a special case of the general. Two cards are drawn in succession with replacement from a standard deck of cards. What is the probability that two kings are drawn? Probability king on the first draw and king on the second draw. Well, the events are independent because of the with replacement. With replacement is kind of another way of saying that you have independent events. We've already seen how in previous video how without replacement is another way of saying dependent events, but with replacement is a way of saying independent events. So probability that two kings are drawn. Probability king on the first draw and king on the second draw. Well, we're going to multiply the simple probabilities because if you're going to replace the king that was drawn in the first draw back into the deck, then all the same probabilities are in order for the second draw. Well, there are 4 kings in the deck, 4 successes, 52 possible outcomes because there are 52 cards in the deck. And so it's 450 seconds for both the first draw and the second draw. Multiplying these numbers, which is really multiplying 1/13 by itself, we get 1/169th. That's probability king in the first draw and king in the second draw if you are replacing the first card. Another situation, 2 marbles are drawn with replacement from a bag containing 7 blue and 3 red marbles. So with replacement again, the events are going to be independent. Probability of blue on the first, red on the second. So you're going to grab out the first marble, put it back in the bag, and then determine a probability for the second event, which is red. So blue on the first, red on the second, and with replacement. Blue on the first, red on the second. That's probability of blue on the first, which of course is 7/10. Probability red on the second, and you've replaced that that blue one that was drawn on the first draw, so all 10 of the marbles are still there in the bag for the second draw, making the probability of red on the second 3/10, not 3/9, but 3/10. So we get 0.21 for the probability of blue on the first draw, red on the second draw, which feels about right. Two events are dependent when the outcome of one event affects the outcome of the second event, or it affects the probability of the second event. Example, 2 cards are drawn in succession without replacement. So the without, that's code, right, for dependent events. Dependent events. From a standard deck, 52 cards, 4 suits, 13 cards each suit. Hearts, diamonds, clubs, and spades. Ace through 10, and 3 face cards in each suit. Find the probability of king on the first draw, king on the second draw. Now that was just 1/169th in the with replacement experiment, but this time, so it was 1/169th in the with replacement experiment, but this time it's going to be slightly different. Now, without replacement, we're still going to have 1/13 for probability of king on the first draw. But after that king has been drawn and not replaced, there are 51 cards remaining in the deck, only 3 of which are kings. And so 3/51 is probability of king on the second draw. And so multiplying 3/51 by 4/52, of course we multiply across, right? 4 times 3 are 12. 52 times 51 is a big number. Of course 3/51 reduces to 1/17. So that might be, and this is 1/13. So that way we can see that we do have the 1/221. 169, and then you had 4 more 13s in the denominator, or 52. So 1/221 That's probability of king on the first draw, king on the second draw, but without replacement. Slightly less likely than in the with replacement situation. Here's a typical problem that you might be faced with in a assignment or in a test. Are smoking and lung disease related? And here are the proportions, the relevant proportions in the 4 cases. If you take any person, the person is either a smoker or not a smoker. The person either has lung disease or does not have lung disease with these probabilities. And it is a legitimate probability distribution. The probabilities all add to 1. So we're going to find the probability of lung disease. Okay, now, are they related to each other? So we're going to take one of those definitions. For example, maybe this one, probability lung disease and smoking. Is that the same thing as the product of the simple probabilities, probability lung disease times probability smoking, right? If so, then we would say the events are independent. If not, not. Probability of lung disease, okay, so this expression right here, that's the first row, and right there we've got your 0.15. Probability of smoker, well, that is first column, and 0.12 plus 0.19, that's going to be 0.31. And now we're going to multiply those two things. That's our right hand side here. And is it equal to the probability of lung cancer and smoker? Well, no, it's not. Probability lung cancer and smoker is 0.12, as it says right here, but that's not equal to the product of 0.15 probability of lung cancer and 0.31 probability of smoker. That's actually kind of close, but the events are dependent because those two things are not exactly the same. Let's see, what would this be? This would be oh, actually it's not that close at all. So maybe that would be about 0.05 approximately, which is not that close to 0.12. And we wouldn't expect these events to be dependent. In real life, we sense that they are very dependent, not independent. You're not going to have any less probability of lung cancer if you smoke. We understand that from everyday life. So, summary of key concepts. Conditional probability, we have those formulas, and you can memorize either one of those. Okay, just make sure that what's second is what you see in the denominator. Given event B, in other words, the universe is that of the event B being prevalent, and so that's the denominator in the probability problem. Okay. That's a condition of independence that we just described. It's not probability of B given A, it's just probability of B if the events are independent. If and only if the events are independent. Here's another form, which is really maybe more of a definition than the first one. This one I would say is useful for doing problems. This one I would say is intuitive. It kind of makes sense as far as what we think independence ought to mean. You know, this B doesn't really matter. Probability of A is just probability of A, regardless of what event B wants to do. There's another form. And here, well, it appears that they're actually just repeating themselves. Oh, they're changing the direction of the conditional if-then. Okay. And then if you have a bunch of independent events, the probability that they all happen, event 1 and event 2 and event 3, all the way to event n. If they're independent, then the probability that they all occur is the product of the simple probabilities.